Okay, so in this problem we have a spherical hot air balloon, meaning that we have a hot air balloon that's in the shape of a sphere. And then it's expanding because air is going inside the balloon. Now what we're given in this table is r prime of t, which is the rate of change. If you notice, the rate of change is first pretty fast, and then as more and more air fills up, it slows down because the balloon is bigger. Another thing we know about it is that it's concave down, and we know that the radius of the balloon is 30 feet when t equals 5. So I want you to think of that as a coordinate. When t is equal to 5, the radius is equal to 30. Keep in mind, this is r prime, not r. The first thing says estimate the radius of the balloon when t equals 5.4. Well, I don't know much. I just know that it's concave down, and I know that there's a coordinate here that's 5, 30. I want to use a tangent line to estimate what it is at 5.4. So tangent line, again, we're always going to use point slope. Y minus y1 equals mx minus x1. Okay? Obviously, it's going to go y minus y sub 1 is 30 is equal to, now the slope is the slope at 5. The slope at 5 is 2 equals 2, and then x minus x1, which is 5. Okay? You can solve for it, or you can just plug in. The number we're going to plug in, because it's asking us, is estimated at 5.4. So we're going to plug that in for x, and you can solve for y. And it turns out at 5.4, okay, y is 30.8. Okay? So in answer to the question, that's the approximation. And is it less than or greater than? Well, you can see that it's greater than, or yeah, it's greater than, because the actual value of 5.4 would be here. And the reason for that is because it's concave up, or concave down. Okay, let's look at the next part of the question. Same thing, except for this time it says find the rate of change of the volume of the balloon. And we're given the formula for volume right here. Rate of change with respect to time. So obviously this is going to be a related rates problem. So I have 4/3 pi r cubed. Okay? When I take the derivative with respect to time, okay, bring the 3 down, obviously, which cancels the 3 on the bottom. So I'm left with 4 pi r squared, but then don't forget dr dt. Okay? The next part is, well, it says find the rate of change of the volume. So I'm looking for dv dt. I need to know r and dr dt. This is all occurring at 5. I know dr dt at 5. Dr dt at 5 is 2. So I can plug in 2. And I also know the radius. The radius is 30 feet at t equals 5. So I can plug in 30, square it, plug it all in, and you'll get dv dt. Part C says use a right Riemann sum, 5 intervals to approximate this integral. Okay, so I'm going to integrate, meaning find the area. Like before, I'm going to use the right hand because it says use a right Riemann sum. So I'm going to go up, over, create that rectangle. Okay, notice I use the right height, which is 0.05, and the base of this is going to be 1. Okay, the next rectangle over, I'm going to go up at 0.6, over, down, create the rectangle. The height of that one was 0.6, and the base of that 7 minus 11 is 4. Okay, actually I got to fix this. This is not 0.05. This is 0.5. Okay, the next rectangle we'll look at will go up to 1.2. Okay, we're going to go up to 1.2, over and down. The height of that rectangle is 1.2. Okay, the base of that is 2. Okay, one more rectangle, 2 more. We go up to a height of 2, over, the base of this is 3, the height is 2. Okay, and our very last rectangle, we'll use this color. We go up to 4.0 and over. Okay, we use black. Up to 4.0 and over. Okay, so the height is 4.0 and the base here is 2. Okay, to find the area of that, you're obviously going to have to add it up. Okay, the rest of this we are going to just do on part 2.